On April 10th, 2019, the world got its first look at a black hole. And it was everything we expected and nothing we expected all at the same time. Let us take a closer look at this historic photo and why it is one of the most important images ever taken. This is M87, and it is the first black hole to have its image captured by the Event Horizon Telescope. M87 is located 55 million light-years away in the Virgo constellation. At the center of this giant elliptical galaxy lies a supermassive black hole with a mass 660 trillion times that of our Sun. That makes it more than 3 billion times more massive than the black hole at the center of our Milky Way, and here it is up close. What you see here is the accretion disk of M87, a glowing disk of superheated matter being pulled into the black hole. The orange and yellow material around the edge is gas being heated to 1 million degrees Celsius. Eventually, the material is pulled past the event horizon, which is the boundary of no return for anything that enters. Once something crosses the event horizon, not even light can escape the pull of the black hole, and it disappears from view forever. The boundary itself cannot be seen because not even light can escape its grasp, which is why it's been nicknamed the point of no return. But the stuff around the edge is glowing so brightly due to the intense heat that it outlines the edge of the black hole like a fiery ringlet, creating what is essentially a black hole selfie. The thing about black holes is that they don't actually look like anything. They are completely black, hence the name. It's their surroundings that make them visible. So how do you take a picture of something that doesn't emit any light? Here's how. Black holes can be detected because as they accrete or consume matter, they emit X-rays. By observing these X-rays, astronomers can determine where the black hole is located. It's the glowing stuff around the black hole that obscures our view of it. To see the black hole itself, we need to block out the bright light coming from the accretion disk. This can be done by using multiple telescopes around the world and combining their data together. By synchronizing the telescopes to work as one, you can effectively create a telescope the size of the planet Earth. This is called an interferometer. In the case of the Event Horizon Telescope, 7 radio telescopes were used across the globe, for in Hawaii, 1 in Arizona, 1 in California, and 1 in Mexico. Each telescope is paired together with every other telescope in the array, collecting data in what is effectively a global network of radio observatories. All 7 telescopes work together to create the largest possible telescope in order to resolve details on very distant objects like the one we saw today. Resolving is a term that describes the ability to distinguish between 2 closely spaced objects. In order to resolve 2 objects that are very far away, you need a very big telescope. The bigger the telescope, the smaller the angle that can be resolved. The smallest resolvable angle is given by the following equation, where d is the diameter of the telescope and L is the distance to the object. If we rearrange this equation, we can see that if we want to resolve a smaller angle, then we need either a bigger telescope or we need to get closer to the object. We know we can't get closer to the object, so we build bigger telescopes. The biggest optical wavelength telescope currently in operation is about 30 meters in diameter. The largest radio telescope currently in operation is about 165 meters in diameter. But as mentioned before, the Event Horizon Telescope isn't a single telescope. It's a network of telescopes that work together. This means that the diameter of the telescope isn't fixed. It's the maximum diameter of all the telescopes combined. So in the case of the Event Horizon Telescope, the effective diameter is about 150,000 kilometers. That's the size of the Earth. When we use the Earth as a telescope, we run into some problems. The atmosphere causes the stars to twinkle and also distorts the image of distant objects. Stars appear to move around and change shape. This makes taking clear pictures of things really difficult. Because of this, the Event Horizon Telescope uses very long baseline interferometry, or VLBI for short. Volby is a technique where data from different telescopes is combined to create one image. The data from different telescopes is collected and synchronized with atomic clocks. This allows the telescopes to essentially act as one big telescope. The telescopes collect data on the exact same instant, allowing the image to be reconstructed without any loss of detail. The reason for doing this is that it allows astronomers to observe things that would otherwise be impossible to see. For example, the structure of a black hole's event horizon or the detailed structure of a distant galaxy. The amount of data collected by the Event Horizon Telescope is staggering. Every telescope collects 5 terabytes of data per day, and there are 240 gigabytes in 1 terabyte. That's equivalent to streaming over 100 gigabyte Steam games every second for an entire year. That's a lot of data to collect, store, transfer, and then analyze. Now that we know how the image was taken, let's take a closer look at what we learned from it. First, the image confirms that Einstein's theory of general relativity is correct. Einstein predicted that light should bend around massive objects. This is known as gravitational lensing. If light is bent around a massive object, then it will also be bent around the event horizon of a black hole. The light rays from the accretion disk are bent around the event horizon, causing the disk to appear larger on the right side. This is known as relativistic beaming. If the disk didn't appear larger on the right side, then this would indicate that Einstein's theory is wrong. But the fact that the disk does appear larger on the right side confirms Einstein's theory. Second, the image shows that black holes do have event horizons. This may seem obvious, but it's actually a really important point. If the image didn't show an event horizon, then this would indicate that black holes aren't really black holes. They would be something else that has a similar mass and gravity, but it wouldn't be a true black hole. This would also mean that our understanding of gravity is incorrect. The fact that the image does show an event horizon confirms that black holes are real and that our understanding of gravity is correct. Third, the image provides evidence that spacetime is not a smooth, continuous medium. Spacetime appears to be made up of tiny cells, each with its own discrete set of properties. This is known as a pixelated or granular structure of spacetime. This is evidence that there may be a deeper, more fundamental structure to the universe. The universe may not be as smooth and continuous as we think. Fourth, the image provides evidence that there is more to black holes than just the event horizon. There appears to be a dark region at the center of the image. This could be the singularity. The singularity is the center of a black hole where all of the mass is concentrated. It's also where spacetime breaks down. Our current theories can't describe what happens at the singularity, so this is an area of active research. Fifth, the image provides evidence that black holes can spin. The asymmetry of the image indicates that the black hole is spinning. This is important because it provides evidence that black holes form from the collapse of massive stars. When a star collapses, it leaves behind a highly magnetized, rapidly rotating neutron star. This neutron star can then capture more matter and become a black hole. The process of capturing matter causes the black hole to spin. Sixth, the image provides evidence that black holes can grow. The black hole at the center of M87 has grown significantly over time. This is evidenced by the fact that it is much larger than the black hole at the center of our galaxy. Black holes can grow by capturing matter. As they grow, they also become more active. This means that they emit more X-rays, making them easier to detect. Finally, the image shows that black holes are not static. They are constantly changing and evolving. The accretion disk is not a static structure. It's constantly changing shape and size. This is due to the fact that the material in the accretion disk is constantly falling into the black hole. Overall, the image of the black hole is one of the most important scientific images ever taken. It confirmed Einstein's theory of general relativity. It provided evidence that spacetime is not a smooth, continuous medium, but instead has a granular structure. It provided evidence that there is more to black holes than just the event horizon. It provided evidence that black holes can spin and grow. And finally, it showed that black holes are not static, but instead are constantly changing and evolving. What do you think of the image of the black hole? What do you think we'll find out next about black holes? Let me know in the comments below. And speaking of what we'll find out next about black holes, did you know that scientists are planning to take an image of the black hole at the center of our galaxy? The black hole at the center of our galaxy is called Sagittarius, a star. Scientists are planning to image it using the Event Horizon Telescope. The image won't be as clear as the image of M87, but it will still be an incredible achievement. Stay tuned for updates on the progress of imaging Sagittarius, a star. I hope you enjoyed this video. If you did, please leave a like and subscribe for more videos like this. Thanks for watching.